Hi, welcome to Microsoft BI learning session. My name is Amit and today I'm going to talk about some of the basic building blocks of Microsoft Analysis Services. In today's session we are going to talk about some basic concepts and the keywords. In a subsequent session we are going to talk about in detail hands-on activities. So this is a complete Microsoft BI solution architecture. You see there are different products into different layers. The complete diagram divided into layer diagram, and I'm going to highlight some of the important terms. So the first thing, you have got disparate data sources. In order to build a BI solution, your data source may be disparate. It may be coming from different sources like customer relationship management, enterprise resource planning, supply chain management, some external source, or it could be some legacy application as well. Enterprise warehouse is a one centralized place where business people can find the required data. On top of this, they can perform some business decision. So we need to pull data from disparate sources, and this is done via one of the tool called ETL, extract, transform, and load. And the product from Microsoft family is SSIS, as SQL Server Integration Services. So this is integration services connect to disparate source system, pull data and store into a temporary place. Temporary location where you play around with the numbers and data, like staging task is like a temporary table where you clean your data, correct your data, and you apply various business rules to ensure that data is consistent. Once it is done, you may put this data into your ODS, that's called operational data source, one common repository where your all business data is available. From staging table you can directly, there are two paths, go over here, you see there's one path, SSIS, directly extract data from staging table and populate your enterprise warehouse. It may also possible your SSIS extract, transform and load data into operational data source, and then you in turn pass into enterprise warehouse. What method you use depends upon the various business factors. We'll discuss about this in detail. Let's take a simple path. So you extract data from disparate sources, put into your staging area, temporary area, and then you transfer back into enterprise warehouse, where your data is logically divided into multiple segments. You have sales data, finance data, global HR data, procurement data, and various other data segments. It may be possible that your enterprise warehouse in third normal form, it's more detailed manner. You may require to pull this data and aggregate this. There's another product used from Microsoft BI family called SSAS. It's called, we also call in general called Cube. So it's another database where you store the data for advanced business analytics you can perform over here. So data is cross tabular view. We'll see this in detail. And finally, presentation of information is done via report. So you see gathering data, data cleansing, data storage, modeling of data, presentation of data, and then you have various tools from Microsoft family to analyze it. You can use reporting product called SSRS, SQL Server Reporting Studio, in addition to SSAS, which would be interface or face to your SSAS cube. And the information can be shared using a SharePoint portal. For your business user who are more comfortable with Excel, they can directly connect your Microsoft product remaining in Excel sheet. There is a couple of points we should be knowing before we start SSAS, especially the comparison between your transactional system, typical transactional system, and SSAS or OLAP cube. See, you have a relation database which is pretty well designed in order to manage your day-to-day transaction. For example, in my Excel sheet, the information recorded in terms of transaction by transaction, it's a sample data from Walmart. So Walmart kind of transactional data where one row is one transaction. So as you go to the shop, buy something, it turns out to be a one transaction. So one transaction consists of which country, which city, which product, what date, who was the store manager, and who bought it, at what time the product bought, and what type of store. So you see the system it is being used by, which is being used by your Walmart, it's like your transactional system. Every time you book your flight ticket, you do your railway reservation, all of them called transactional system. It is more generic called OLTP, online transaction processing. When you already have online transaction processing system, then why do you need an OLAP? OLAP and OLTP are two different worlds. OLTP designed for transactional processing and day-to-day transaction. It's a backbone of your business, whereas OLAP is designed for your analytical needs. In one simple line, OLTP is your insert, update and delete, and OLAP is your select operation. So generally when you work in BI domain, you do not have any control on OLTP. It's a complex software, could be sales order processing, railway reservation, ticket raising. It's a complex software, and we do not have control to customize and modify it as per our BI need. OLTP data is extracted from OLTP and then put into my OLAP solution, and your all business queries, analytical query will sit on top of that, all the analytical query. So when you pull data from OLTP, you may need to export, clean the data and integrate from disparate sources to a common place. So maybe you have got one OLTP system for sales order processing. You may have one OLTP system for your HR system. So you may have multiple OLTP systems which may require to be integrated and push into a common OLAP. As I said, we have no control on OLTP system. Therefore, all the modification required, I need to design solution to accommodate those changes in my OLAP. OLTP is as is with no changes. It may also be possible the data available in your OLTP is inconsistent, may not be appropriate to put into the OLAP system directly, and therefore every time you pull OLTP data to OLAP, you may have some sort of data cleansing layer or data scrubbing layer. OLTP primarily designed to perform day-to-day business operation, which is whereas your OLAP is not designed for day-to-day business operation, it is designed for analytical needs. So we need to understand both of them are two different worlds with different needs in mind. If I directly build my solution on top of OLTP, any BI solution on top of OLTP, we have to face a severe performance problem. So all the business queries are built on top of OLAP. That's another brief diagram which talk about an integrated view between OLTP and OLAP. OLAP is often subject specific. As you see in my diagram, I can disparate OLTP system, transactional system. We put them into common repository which hold the historical data called data warehouse, and then from here we put into our data marts and OLAP. Basically data mart, OLAP is a data mart. Data mart is a subset of data warehouse, subset, which is subject specific. So maybe my customer like to design my whole business in terms of various subjects. They want financial analytics, they want sales analytics, and similar kind of analytics they want. So each analytics we can create a one OLAP system. In order to design an OLAP system, there are a couple of keywords and definition we should be knowing. OLAP, online analytical processing. There are two important terms we should be knowing. The first is called dimension and facts. Your transactional system store data in terms of tables, whereas OLAP store data in terms of dimension and facts. The easy way to understand dimension and fact, dimension define the context and facts are number. So in which context you are organizing, you're analyzing your facts. If you ask any business query, it can be split into dimension and facts. Take any business query. For example, like looking at my data, I like to see business user want to analyze month-over-month sales growth, month-over-month sales growth, for product category A and B, right? So what I need to analyze? I need to analyze sales. Sales would be my measure, or a facts. Facts are numbers, is sales. And in which context? In the context of product A and B for each month, right? So month is my dimension. So any query in turn split in terms of dimension and facts. I can give you more detailed view of it. Now look at this visualization view. This is a transactional model, transactional system, which may not be designed appropriate for your query and analysis. So we divide this model into different view. That's called dimensional view. A dimensional view essentially consists of dimension and facts. You see my data is organized in terms of dimensions. My dimension is province or a city, and dimension is time. So with respect to province and time, I have got a data which is sales. It's a two-dimensional view. It could be three-dimensional view as well. You see you have got sales manager, two sales manager, John and Mac, and different province and different time. Intersection of your province with your sales manager and time is your data. So you read this sales is New York Q1 sales done by John, right? So information is essentially organized in terms of dimension facts. And in order to design a Microsoft BI cube, AS cube, we need to divide our into three pieces: dimension, facts, and attributes. Attributes are like characteristics of any object. Like product is a dimension. The attribute of product could be color, size, font, color, size, weight, and all. And consumer type. Some attributes, some characteristics about the product. So when you design an OLAP solution, the first step you need to design your model. I'm going to show you graphical presentation of tables. That's called dimension. You see, we divide the whole model, our transaction system, in terms of subjects. My current transaction system doesn't contain any subject. Right? It's one row is one transaction, which we can understand as product, province, store is one object, and you have got facts like operating cost, sales, and all. The same information we presented in a cross-tabular manner called pivot. You got sales manager, province, and time. So in the whole model, we divide our table in terms of dimension, which talk about subject area and the facts, right? This is how it graphically look like. I have got a couple of dimensions and facts, and somehow they are related using primary key and foreign key relationship. Let's get into more detail. So data would be organized in terms of dimension fact as opposed to in terms of tables. So facts, as I said, by definition is the numbers which can be used for any kind of analysis, right? But the facts are numbers which bring certain business meaning to the user. For example, I say what is fact? We can apply fact test. So your facts could be sales, revenue, margin, and age. Is age fact? Is age fact? We'll test it. The simple test is this: when you look at the fact with respect to some dimension, if it brings certain meaning, then it's a fact. For example, I'm looking at my fact with respect to my time dimension. So if I see time dimension sales, time dimension with respect to sales, January sales plus February sales plus March sales. When we apply aggregation of them, it brings a meaningful information to me, Q1 sales. Yes. So aggregation of sales with respect to time dimension brings certain meaningful information to me. Therefore, sales is a fact. Whereas age, or I say another number, social security number. If social security number, if we aggregate them with respect to some other dimension, it may or may not bring any meaning. For example, I say John's social security number plus Carrie social security number. It doesn't bring any meaning. Therefore, it's not a fact. I assume SSN is a number, completely number. Similarly, if you add John age plus Carrie age it brings no meaning. So facts are numbers. When you aggregate them with respect to dimension, if it brings certain meaning, it's a fact, otherwise it's a dimension. So dimension are qualifying characteristic that provide additional information about facts. Qualifying characteristic. Now look at this. This is your fact. When I look this fact with respect to my dimension, I would say with respect to one dimension, it's a Q1 sales. Right? I would write it's a Q1 sales. When I look the same thing, it's a Q1 sales. When I look at the same thing with respect to my other dimension, it's a Q1 New York sales. So as I'm adding more dimension, it is bringing a different meaning to my facts. Additional perspective or view towards my fact changes, depends upon in which context I'm looking. So context change my fact meaning. It's Q1 sales, it's a Q1 New York sales. This is Q1 sales whole, Q1 sales. This one is Q1 New York sales. So that's what your fact define. Your attributes or your characteristics define property about a specific dimension. Attributes like your customer attribute is, your product attribute has product attribute, could be product size, color, consumer type, and so on. The dimension fact has to be organized certain form. In your relational database, you must have heard of you organize information in terms of ER model, entity relationship model, where it consists of entity and relationship between entities. But in a multidimensional model or OLAP, the information organized using star schema or Snowflake. So star schema is a relational database schema for presenting multidimensional database. It's a simplest form of data warehousing schema, which may have one or more fact tables, which may have one fact table. Let me correct, one or more dimension and one fact table. This is show you one of the simple example. This one could be my star schema. This is a star schema. Look at this, which has got one fact table in the middle and surrounded by dimension. As it looked like a star, therefore we call it a star schema. It's a fact table in between and dimension surrounded by. And you see star schema, it consists of facts table and dimension table. And each dimension table consists of specific subject area, like product dimension has got product detail, store dimension has got store detail, period dimension has got time detail. And the key which join between dimension fact is a primary key. From your dimension table to the fact table is a foreign key, primary key and foreign key. So fact table consists of foreign keys plus numbers or measures, and dimension contain primary key and various column or attributes of a given dimension or members. So star schema organize them. We use a star schema is easy to understand and fast in performance. Because it looked like a star, therefore we call it a star schema. It essentially has one fact table and can have multiple dimensions. And each dimension is highly denormalized. This is highly denormalized. Look at this. This is store dimension. I can split this store dimension two pieces. This got normalization. When you join them, it's called denormalization. Right? So it is essential you have in a star schema you have each dimension is highly denormalized, which cannot be further denormalized, and here should be one dimension of one subject area. The star schema has the biggest advantage, which we'll see practical in subsequent session. The first advantage for performance. The star schema is higher in performance, and it can allow you to do data in a detailed and summary manner, plus sliding, slicing and dicing. You can do drill down and drill up. These are some keywords we are going to see in a subsequent session. So performance is relatively higher. As you see, I'll show you, demonstrate. The performance of the query depends upon the number of join it has. Right? In model, this is my star schema. Every time in order to bring the data from this table, in order to bring data from this model, I need 3 joins. 1, 2, 3. If I normalize one of my store dimension to store in region, I need 4 join, 1, 2, 3 and 4. Therefore in a star schema, it's expensive and slow in process. Star schema is fast in performance, whereas if I denormalize it, the performance increases. If you normalize, performance decreases in terms of query performance, and it is easy to understand. That's another example of graphical presentation of your star schema. Single fact, multiple dimension. No dimension can be further normalized. Two important keywords. Snowflake schema is an substitute, another alternate for star schema. Snowflake star schema used in two different contexts. If you want write back, our requirement could be pretty straightforward. We use star schema when you want fast performance. You want fast, you want performance, fast query process, you want better performance, and your requirement is report only. You are designing a reporting solution. But on the other hand, the star schema has difficulty. It's difficult in insert, update and delete. Also, star schema is not appropriate. It has large number of duplicates. It is not appropriate for write back operation. Snowflake gives little flexibility in it. Snowflake model is appropriate for, it is relatively good for insert, update and delete operation. Relatively slow, one has to compromise with the performance, but it has got relatively less duplicates. Right, so we would prefer to have we would prefer to work directly on star schema when it comes to MSBA solution. We don't want the model to be highly normalized. The more normalized it is, the difficult it is to query. So it's pretty simple to see that. Look at it. This become my star schema model. This is my star schema model. Star schema. There is only one dimension for each subject area. When I split this to two pieces, this becomes a snowflake model. Star and snowflake. This is denormalization and this is normalization. Right. Important consideration when you're designing a solution, Microsoft SSAS Cube, we prefer to have a star schema. Therefore, many of time we get snowflake schema as a requirement. We need to convert it into star schema. So we denormalize each dimension to the greatest extent so that there can be any further denormalization, and it turns out to be a snowflake star schema. We can directly build our solution on top of snowflake schema, but one has to incur the higher cost. The cost would be relatively high. I can convert, you may have even more complex model called a galaxy model, which is one step further. The galaxy model may have multiple fact tables and multiple dimension. Let's see this example. This is a galaxy model of fact. In this galaxy model, there are two fact tables and many dimension. The dimension which share between the fact tables are called confirmed dimension, right? And so what I can do logically, I can split this model in two logical pieces. So my one confirmed dimension would be, this could be one star schema. I split this one piece of it. It turns out to be a star schema. Well, I would assume that I'm going to denormalize this. I'm going to denormalize this like this, and custom and country denormalize, it turns out to be star schema. So let it be snowflake. You split this model into pieces. This is one star schema, and I take a snapshot of this once again, and from this part I'll cut this piece. This becomes another star schema, right? So whole galaxy model split into two star schemas, or one star schema, one snowflake schema. That could have done. So create a separate model. We create a separate model to split the Galaxy model into star schema and snowflake schema. We use the confirm dimension to identify how to join them back. Confirm dimension is a common dimension between two fact tables. So you gather all this requirement before you start building your Microsoft SSAS cube. You're supposed to have a list of dimension, attributes, hierarchies, and the respective properties. Another important thing is like junk dimension. It may possible you have junk dimension. I'll first show you the concept of junk dimension. In a ETL concept, we call them lookups. Okay, so you see there are junk dimension, simple structure that provide a convenient place to store junk attributes. It is just a collection of random transaction codes. Maybe I'm designing sales order processing. One of my dimension is product. So product has got product color, product material, product size. There could be additional information about my product, right? So I club them together and form them as a junk dimension. It's a simple structure, as the definition says, a simple structure that provides a convenient place to put your junk attributes. So you should identify what are the junk dimension members you have in the initial phase of your design. Next step, you may also have a degenerated dimension. There's another concept. A degenerated dimension is a dimension key without corresponding dimension. What you see in your example, in my model, that each dimension has corresponding foreign key in a dimension table, in a fact table, sorry. If I talk about this, each dimension has a corresponding foreign key in a fact table, right? It may possible there are some member which doesn't point to any dimension. Any member in my fact table which doesn't point to any dimension, that called degenerated dimension. What it mean? In this example, assume my fact table called retail sales. So I can identify my sales based on supplier, based on product, based on store, based on employee, and based on time. There's an additional dimension member over here called bill number, and it is not pointing to any other dimension. Right? So I can group products based on bill number, and bill number is not a foreign key with respect to any dimension. It is a degenerated dimension. If you have a degenerated dimension, the cost of query would have gone very high. So this is done in order to save the space. Once you design your cube, it may possible your underlying data source system changes, which is very common. Your enterprise data warehouse continue to have changes, and we like to have a track of these changes. So there's a concept we call slowly changing dimension. A dimension attributes or a value which change slowly respectively and accommodate all the new updates called slowly changing dimension. How you accommodate the changes into your underlying system. There are three kind of, that is called in short SCD, SCD 1, 2 and 3. In SCD 1, what we do, in SCD 1, we accommodate the changes. If the new value comes, this is the old value and this is a new value. If new value come, we override the new value on top of old value. So I got a new value, I override on top of old value. And this way we do not maintain history. We maintain only latest value and we do not maintain history. But there's a column called last updated, we modify. Last updated says when changes were taken place. So SCD1 is a simple way, whenever new value comes, we overwrite it. In this example, product description got changed, so we override product description, remaining other properties are same. But if somebody asks me to go back and tell me what was the previous product description, I don't have those details. In SCD Type 2, we maintain the history. How do we do that? Every time we get a new value, new record, we keep the old record as it is and we add another row with new surrogate key value. right? And we have a start date and end date. Start date and end date say the life of a record. So this record was active from 1st March to 15th December, lives of this record. Second row says the same record got modified and there is no end date to the same because the record is live. So wherever end date is empty, it's a live record or current record. So you see in this example the contact number got changed. Even I can go back and see the old contact number because I have not deleted the record. Slowly changing dimension type 3. We want to maintain old value in an additional column, right? For example, here the phone number got modified. So I add an additional column and old phone number we maintain over here, current phone number and old phone number. This is also you need to consider what degree of details you want to maintain. So I'm maintaining only one level of old phone number. If my phone number modify 5 times, then we override them. We add a new row and keep on adding this number. Finally, it may also be possible that your underlying source system has got bridge table, or you may need to prepare a model with factless fact table. A factless fact table, as the name indicates, it's a dimension intermediate which doesn't have any fact. It just contains a foreign key. Let's take a simple example. So I'm going to talk about a simple example over here. Let's imagine you have a dimension table called salesperson, right? You have one dimension table called sales manager. Okay. Sales manager, which consists of salesperson ID, salesperson name, and salesperson ID, salesperson name, and which deal he was involved into. There are many business deals. Okay. So assume your salesperson ID and business deal. This is my metadata structure. I've got another table called business deal. So let's load some record 101. John is a salesperson, 101. Salesperson name is John and he was involved in 2 business deal. Let me store the value over here for business deal. I have got a business deal over here where I have a column called deal ID, deal amount, and who has done this? Salesperson number or ID. So John has done 2 deal. John has done 2 deal, deal 101 and deal 102. Deal 101, deal amount was $100,000 and it is done by salesperson 101. There's another deal called 102, again done by John. John has done 2 deals and the cost of deal amount of $200,000. There's another Carrie. Carrie has another salesperson called Carrie, which has done 2 deals, D101 and D103. So D101 is done by 2 salespersons, Carrie and John. So I write D101 and 102. This is an appropriate model to talk about many-to-many relationship. One salesperson done many deal and 1 deal done by many salesperson. Right? John has done 2 deal, right? And 1 deal done by 2 salesperson. It's called many-to-many relationship. We cannot have many-to-many relationship in your relation database, which causes a Cartesian product. So we can add an intermediate table between both of them, and that's called factless fact. See this? I take sales manager. I keep only 2 records, salesperson and salesperson ID. Similarly, I keep only 2 records over here, deal ID and deal amount. And this is my sales manager table and this one is my deal table. Business deal. Now what I do, I'll take a common column from both of them and keep into a common table. That's called factless fact. I call factless fact. So I cannot use this model directly, so I designed to prepare a factless fact table, and I keep all the common column, both of them. This becomes primary key over here, this becomes primary key over here. The corresponding foreign key I add over here. So salesperson ID, the foreign key, which consists of one salesperson 101, done two deal D101, D102, right? Salesperson had done two deal. Similarly, deal 101 done by two salesperson, 101 done by two salesperson, John and Carrie. So this is a factless fact table which has only foreign keys. It doesn't have any fact. Right? This becomes factless fact. I can turn it, this turns out to be a bridge table in case I add a fact in it. Now why do we need a bridge table? In this example, if I ask simple question, my question is, what is the contribution percent of John? What is the contribution of John? We don't have any answer because John was involved in two deals, D101 and D102. I have no way to manage or maintain information about what is the contribution percentage. Assume John contribution was 30% in this and Carrie contribution was 70%. It may be possible, right? But with my current system I don't have any information. So to maintain this, I can add another column called weight factor, which talk about what weight associate with them. So let's say salesperson 101, which is John, in first deal his contribution was 30% and Carrie contribution was 70%. So add a weight factor which talk about some information. So now my factless fact turns out to be bridge table because it contains facts. So you see the difference between factless fact and bridge table is only one. If the factless fact table contain only foreign key for the respective dimension, whereas bridge table, in addition to facts, foreign keys, it also contain facts. So whenever you get a man-to-many relationship, you need to simplify them. It may also possible there are different kind of transaction table. What kind of transaction table you are using to design your solution? It's good idea to know a little bit about it. Your transaction table could be fact table, could be transactional table. Right? What transaction table is pretty simple. In case your the fact table getting added one row with each transaction, that's become a transaction table. Transaction fact table. For example, I see this is my sales data, right? Let's take this example. This turns out to be my factless fact, transaction fact table, sorry, where if I use store ID and I use bill ID, or I simply keep it, I delete this one, and bill ID. So in bill ID B101, there are two products. In B101 there are two products, so I use the product ID as well. In this bill there are two products are sold, P101 and P102. The moment transaction happen, a new record added in this fact table. This fact table contain foreign keys and facts. So the moment transaction happen, a new record added. This is called transaction fact table. Whereas let's look at the another fact table. I have got a snapshot fact table. A snapshot fact table contains the situation at a specific point in time. Snapshot is a recording of a specific situation at a point. So a simple example could be, you have a fact table over here. I make it. I turn this fact table into my snapshot based fact table. Okay. I assume I have got a stock in hand, right, and certain time period. Stock in hand, certain time period. So my quantity in hand, stock in hand, and I use a time period. At 9 o'clock in the morning, this was my stock. At 10 o'clock in the morning, this is my stock. As transaction happening, at particular time transaction happening, my stock is getting changed. Stock in hand. It was 100 quantity of X product. I use the product ID. This product ID has got this quantity. So it's difficult for me to keep track of my stock in hand and specific point in time. So what we do, we create a snap bucket of it and say, in the morning, I'll bucket of them, create one whole bucket up to 12 o'clock PM. My stock in hand, that's a snapshot of one day. My stock in hand, I'll not keep up to 12 o'clock. My stock in hand would be $100, right? I'll make it central. Up to 12 o'clock, this is my stock, right? Then 12 to 5, what is my stock? I'll take a 2 snapshot of my data. I'll not maintain in every minute. At 5 o'clock, my stock remain 30. So we are capturing the status on specific point in time, and that's called a snapshot. Another example of you get a credit card statement, right? You get your bank statement. So at the end of the day, you get your assets or total cash in hand in your hand. Total cash in hand, you have cash in your account. So you got two kind of transaction table: snapshot based fact table and transactional fact table. You need to assess what kind of fact table you are working with. Then we use some common terminology or keywords, like you must have heard of primary key, foreign key. There are additional keys we are going to talk about. One is called your basic term. We use key. A key is one or more data attribute that uniquely identify an entity. A simplest example, you have got unique key. When you create relation database, you use a term called unique. So unique key may not be primary key. It's just a unique. We uniquely identify individual row. That's called a unique key. A unique key may be consisting of more than one key. Therefore, it's called a composite key. For example, my unique key is student roll number. Right? Student roll number is my key. My composite key, my unique key is student roll number is unique in a class, but roll number is not unique in a school. To form a composite key, I'll say student roll number plus class number or class name plus class number, and combination of student roll number plus class number, standard or section ID form your composite key. Surrogate key is also kind of key which has no business meaning, right? It is just a key which we add every time the record gets modified. The right example is in your SCD2. So you see vendor key could be a surrogate key. I added one surrogate key every time records are added into my system. And some of the key are self-explanatory. You must have heard of primary key. It is unique and define the primary key and foreign key relationship. Referential integrity constraints. Foreign key and primary key are used in a primary, parent table and child table as referential integrity constraints. So every time you delete records from primary key, foreign key, if the values that exist in foreign table, it doesn't allow you to delete. You have to delete the value from foreign key table and then delete it from primary key. So it enforces you not to delete the value, not to add the value for the respective member does not exist. In addition to primary key is unique. Alternate key could be secondary key, maybe you use sometime. In addition to your primary key, you want another key to uniquely identify your members. You can use foreign key and alternate key as well. So these are some basic keywords we understood today. In next session, we'll do hands-on and we'll take our data source and start building MSBI solution. So thanks for joining today's session. Should you have more questions, please feel free to visit our site or write to us. Thank you and have a good day ahead.